presentation is upon this rock, the geology of Mount Independence, and we're so delighted to welcome back geologist Helen Mango, who's been at Castleton, well, all the iterations of the name, right? For all these years. So
not since the normal school, no.
Oh. One of my grade school teachers was graduated from the normal school, I will say. So, and she's done a number of guided geology walks here over the years, and this time she gets to be inside. So she's going to start us with the ground of Mount Independence. So thanks so much, Helen. Welcome back.
I feel a little out of my native habitat, you know, because I'm usually looking at rocks. And when I thought about doing this today, when Steve had suggested, well, maybe you could, you know, talk for 20 minutes and we can go out and look at rocks. So today it would be, you see this wet gray rock and then that wet gray rock. So best probably to use slides that were taken on much nicer days. I mapped the geology of the Orwell quadrangle, so 7.5-minute quadrangle back in the 90s. And it is a deceptively difficult place to map rocks because the territory, you know, you've got these lovely rolling meadows and whatnot, and there's very, very little outcrop or ledge in a good deal of the town of Orwell. There are some places where there are some good outcrops, and thankfully one of them is Mount Independence. So one thing that you can sort of tell just from this picture taken from Mount Defiance is that there is a certain amount of topographic relief on the mount, which of course is why it was used for its much later purposes, but that means that geologists like me can actually find rocks to look at and figure out what the geology of the area is. So it turns out that the geology is very, very different from where the photographer was standing for this picture to the mount, which is related but different from the middle background here, the forest and fields of Orwell, and then different again from the Green Mountains in the background. So what I'm going to try and do is give you a very brief synopsis of how a geologist looks at the rocks and figures out how the rocks formed and how they got to be in the position and orientation that they are today. So, this is a geologic map of the state of Vermont, and one thing which I think is very obvious is that this is greatly simplified, for starters, but you can see that the bands of similar types of rock are oriented in mostly a north-south direction. So you get these elongated bands of rocks. Here are the Taconics, these are the Green Mountains, and then this is the Champlain Valley. So we're going to be focusing in on this area because there's Mount Independence right there. So the north-south orientation of these bands of rock is due to the fact that a good deal of Vermont, and very subtly in this area, was greatly affected by big mountain building events that involved continental collisions. So continents coming together, closing ocean basins, and then crashing together in very, very, very slow motion, and in the process metamorphosing rocks, crumpling them, folding them, changing them, creating igneous rocks, volcanoes, all kinds of exciting geology. We're right at the very, very far edge of that. And so the only evidence that we have in western Vermont here of events that were taking place to what is now the east are some faults. And there are a number of mountain building events and other big scale tectonic events that have alternately pushed rocks together and pulled them apart, and has allowed for the rock in that process to crack and move in directions, so big pieces of the Earth's crust moving relative to each other, up and down, side to side, over and under, and that's really the extent of those big tectonic events that we see around here. So they are a little part of the world here. So everything that's in this light gray color are sedimentary rocks, so rocks that formed through deposition of little particles or through the activity of marine organisms. And they are all of Cambrian and Ordovician age. So these are the geologic time periods, 2 out of the big geologic time scale. And so in millions of years, we're looking at rocks that formed from about 550 million years to about 450 million years. So that's all of the rocks in this gray area, and we've got a portion of it here in Mount Independence. So there is one large fault called the Orwell thrust, and a thrust fault is a fault that is at a low angle, and it pushes one mass of rocks up and over another at a fairly shallow angle. This is only one, and it sort of joins in with what we call the Champlain thrust. This is only one, or it's the biggest one of many, 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 many other faults through here. But on the scale of that map, they only put the really largest, most obvious ones. But this whole area is just crisscrossed with faults of various kinds. They don't move anymore because they formed a very, very, very long time ago, and the forces that made them move are long gone. But they did alter how the rocks are broken up and moved relative to each other. So we're just going to stick with these sedimentary rocks of Cambrian and Ordovician age, so just think 550 to 450 is good enough for our purposes. So how do sedimentary rocks form? Well, 2 major mechanisms. One is rocks like sandstone. So here's just a piece of sandstone. There's a close-up of some sandstone. You probably all know what sandstone looks like. Sandstone forms when little particles of a certain size, sand-sized particles, accumulate, so they erode off some rock mass. They get transported, usually by running water, sometimes by wind, accumulate in places, and then if those sand grains get covered by more and more and more and more, and solutions percolate through that contain dissolved minerals that precipitate, stick those sand grains together, you form sandstone. So sandstone forms in 2 main types of environments: deserts and beaches. We have evidence that the sandstone that is around here is not a desert sand, but rather a beach sand. And I'll get into what some of those pieces of evidence are. So the sandstone that is found in this neck of the woods is Cambrian, so about 550 to 500 million years old. And so I was looking around for pictures of what a Cambrian beach might have looked like. And so I Googled empty beach, because we can't have any picture, certainly no land animals of any kind, and we can't have any land plants either, because there weren't any land plants until quite a bit later, more recently. So I took a picture and I cut the people out. And so this is what a Cambrian beach might have looked like. Water, beach. End of story. So there were organisms that were living, certainly many, many, many organisms in the shallow water. As I'll show you, this part of the world, this continent that we now have here up at like 42 degrees north latitude, was much closer to the equator. It's moved since the Cambrian. And there were organisms that also lived in the littoral zone, so between low and high tide, worms and other organisms that were in the sand, as long as it was wet, but nothing was really living up at the top at this point. So we've got some sandstones here. The other rock type that we have here is limestone and a related rock called dolostone. If you are into chemistry, limestone is made out of calcium carbonate. Dolostone is calcium magnesium carbonate. So you add some magnesium into the mix and you get what's called a dolostone. We're not entirely sure still at this point in geologic thought how limestone turns into dolostone, like where that magnesium comes from. It seems to be a post-depositional feature. For our purposes today, it doesn't matter. We just say that limestone and dolostone are very, very closely related rocks, and we do know that limestone forms where you have a lot of organisms that make their shells out of calcium carbonate. So organisms like, you can think of clams or anything with a shell, squid, that internal one, anything that might have lived in the past or in the present that makes shells, algae. So there's lots and lots and lots of tiny, tiny microorganisms that live in the world's oceans and have for hundreds of millions of years, microscopic, but they make their teeny little shells out of calcium carbonate. They have the ability to take dissolved carbon dioxide from the air, dissolves into the water, and they can take that carbon dioxide and dissolve calcium that's weathered into the ocean from rocks, combine it, and make their little shells out of it. When the organism dies, the soft, squishy part of the organism, the shells remain, and if they accumulate over time, you get limestone. So the pictures that I have here, these are actually from the Fisk quarry up on Isle La Motte, but it is a very beautiful limestone quarry, so it's very photogenic. There are not the kinds of fossils here that one might like if one's doing geologic mapping and trying to figure out how old a rock is. I'll get to that in a moment. But we do have evidence that these are of similar relationship to the kind of environment where all of the limestones in Vermont were forming. So here's a picture, an artist's rendition of what the Ordovician seafloor might have looked like. And if you compare it to the beach, you can see there was an awful lot more going on in the Cambrian and in the Ordovician. We've got a variety. This is a squid or octopus-related creature, a nautiloid. There are all kinds of different corals. There are trilobites, if you're into fossils, all kinds of different organisms. So the shallow marine environment at this time was just teeming with life, and a lot of that life left behind their shells and made a lot of limestone. So those are pretty much the rocks we see around here. But let's think about, well, how do we know how old rocks are? So one way that we do this is what we call relative age, which is simply that if you have, it's just an older than or younger than kind of thing. So if I say that my brother is older than me, that's a relative age. You don't know how old I am, you don't know how old he is, you just know that he's older than me. In the case of rocks, we can use various sort of logical things, like if you have one layer of rock and another layer of rock, absent something weird happening to it, we assume that the one on the bottom is older, that it had to have been there already when the one on top was deposited. So we use very straightforward principles, logical principles like that to say this one's older, this one's younger. So here's a beautiful outcrop up in Burlington at the Salmon Hole, and that rock up there is younger than this rock down here because it's sitting on top of it. Here's a less beautiful picture just because of the shadows from the trees, but from the Southern Defense Trail, we've got layers of rock here that are sitting on layers of rock here. Those are younger. Now, you can mess with this if you have a fault that pushes rocks from one place up and over other ones. So if you don't recognize that there's a fault between them, you might get caught unawares and actually have an older rock being pushed on top of a younger rock. And that actually did happen here. It's just kind of subtle. But for the most part, we start with the simple, and then you can get more complicated as you need to. So that's one way of figuring out age. And then there's absolute age, which is how old exactly, like in years, something is. So one thing that we use in sedimentary rocks is fossils, where we have them. And as I said, there are good reasons to correlate the rocks with no fossils here to rocks that do have fossils elsewhere in the region, in the other parts of the Champlain Valley and in New York State. So we use correlation with similar rock types to figure out this is like that, and we know how old this one is, so we know how old this one is. Nice mathematical tautology there. The other way that we can get ages of rocks don't apply here, so you've probably heard of things like radiocarbon dating, and there are other ones that, other radiometric, using radioactive elements in minerals. These rocks simply don't contain those minerals, so we can't use those methods. So we have to use other methods to get at the age of these rocks. But we do have a pretty good idea now how old these rocks are, again, the Cambrian and Ordovician. So the other thing that is really helpful for figuring out the geology that I alluded to is simply the topographic relief. So if you look at this area, so I just nicked this off a Google Maps terrain map, which is why there's some advertisements I couldn't get rid of. So here's Mount Defiance, and there's Mount Independence. And one thing which you can see very obviously is that there are a couple of very steep changes in topography. So one right here at the base of this mount, and then of course the one right here, which is sort of separating Mount Independence from this much flatter terrain just to the east. And so when a geologist sees this kind of thing, two things occur. One, the rock that is sticking up is much harder than the rock around it, so it resisted erosion, so the softer rock gets eroded more. And then the other is that maybe there is a fault which is actually uplifting some of the rock relative to others. So it might be a combination of the two. If you get an uplifted section of hard rock, that'll give you an even bigger amount of topographic relief. So you can get some hints on the geology just by looking at the topography. So this is a close-up of and it's blurry because the original map is huge, a close-up of the very detailed geologic map of Vermont. So this one, the more recent one, was put together in 2011, and I'm happy to say that my little corner, my Orwell quad, was incorporated into that map. And this was put together over about a 10-year period by people from the Vermont Geological Survey and the US Geological Survey. And so this is just a little teeny close-up of, again, here's Mount Independence, and then the rocks just to the east, and then I'm going to fill in a bit on the west because the New York rocks don't show up on the Vermont map. But what we have in Mount Defiance is metamorphic rocks that we will connect to the Adirondacks, loosely defined. These are super old rocks. These go back, these were metamorphosed 1.1 billion years ago. So these were rocks that already existed. They probably are 2 billion years old. And they were metamorphosed 1.1 billion years ago. And these are rocks that you see in the high peaks of the Adirondacks. Very similar relationship. Very, very different from what we see just this far away in Vermont. So here we have our Cambrian and Ordovician rocks, and there are more Cambrian and Ordovician rocks just to the east. And you know, when you drive off the mount, you go down that very steep little drive, right, and down to the road there. And then as you're driving back into Orwell, you go across very gently rolling until you hit a steep little hill just before Bascom Road, where there's the Ledge Farm on the north side. So that's the Orwell thrust fault. So you've just gone up and over and back into a different set of rocks. So the flat area are largely limestones that don't have any outcrop at all. So there is, to make a map like this, you find an outcrop over there, and you identify the rock, and you find an outcrop over there, and you identify the rock to the best of your ability, and then you use what we call geopoetry to fill in what's in between that you have no evidence for. So these lines here are somewhat a figment of my imagination, but they're a logical figment. And nobody can prove me wrong because there's no rock anywhere to look at. So anyway, you can see that there's a change in the pattern between these are different limestones here, and they're all gently tilted at an angle, which is why when you erode off the top, as you're walking along, you go from one rock type into another, because they're tilted slightly, as are the rocks of the mount. These are tilted in that direction. These are tilted in that direction, so more to the north. This is more to the northeast, and they're different rocks. They're related. They're all sedimentary. Most of them are limestone or related rocks, but these are somewhat younger and just formed in a somewhat different environment originally, and then they just got brought close together and chunks got broken, twisted, shifted, and now they are actually touching. So we have the two major, what we call normal faults. A normal fault is a fault where you get up and down movement, and one block of rock rises up and the other one falls down. That's what we call a normal fault. Reverse fault goes the other way. So there are these two of these down-dropping kind of faults. There's one just here to the east of Mount Independence, and then there's a really big one right here. Remember that very distinct break in the slope at the bottom of Mount Defiance? A very, very major one that is basically lifting the Adirondack rocks compared to the rocks of Vermont, very close by. So somewhere right here or somewhere right under the lake, there's a really, really, really big fault that has brought these very, very old Adirondack rocks up relative to younger, still old, but much younger rocks in Vermont. So it's kind of a complicated picture here. But right here on the mount, what we have are these gently tilted layers with the oldest rocks at this end and getting progressively younger at this end. Again, if you have rocks that are layered and you plane off the top, you can walk up in age, starting at the oldest ones and then going to the younger ones. They're just sitting on top of each other. There is a little complication down here. I think that there's an older fault there that's repeating some of the layers. Again, in the eye of the beholder. But the general picture is oldest at this end. This is a sandstone, and then we get into the dolostones, limestones as you go in that direction. So just a wee bit of geologic tectonic history, just for the rocks that we see in this immediate region. So this is going back 750 million years ago. This was the end of a big, big, big mountain building, supercontinent forming tectonic event that created, in this neck of the woods, a huge mountain range that we call the Grenville Mountains. And we have the remnants of those in the Adirondacks. So before our sedimentary rocks formed, way before then, we had this really big continental collision, big, big, big mountains forming. And then there was a period, let's see if that's what I've got next. Yes, so the rocks that are the leftovers of that mountain building are the Adirondacks. So let's look over here first. The Adirondacks, the Green Mountains, the Berkshires, what are called the Hudson Highlands through here and then down farther along. You can look on a bigger map here, and there are rocks of this age that roughly either at the surface or we know they're below the surface stretch all the way from Canada, down into Mexico. Actually, this was a gigantic mountain chain. It's been a long time eroding. So at least 200 million years at this point was just quiet, no more pushing together, so it was just sort of stasis, a lot of erosion, and then that continent started to pull apart. It cracked and pulled apart and drifted and formed a new ocean in between. So to keep us knowing where we are, so the yellow dot is always going to be where we are right here at Mount Independence, so you can see that we're kind of right on the edge of the Adirondack rocks. And the Green Mountains, remember in that first picture, we saw them in the distance. They're not that far away either. So this is what is called a paleogeographic reconstruction, which just means that we go back in time and figure out what do the continents look like and where were they, based on evidence that we find in the rocks today. So this is what we might call a normal map, which is a view of the Earth where we think the continents used to be. So we've got these continents, so this is the remnants of that big supercontinent, and the pieces are starting to pull apart. So we've got we are at the edge right here. So this piece and this piece used to be together in what's now our area, and they're pulling apart, forming an ocean. And if we take this continent, this is the core of North America, if we take that continent and rotate it so that it faces north, so that it looks like it looks to us on a map now, we get this. But note that the equator which is cutting pretty much right through this continent, is now, because we've rotated the continent to go north, now the equator is doing that. So we're just taking the whole thing and just rotating it so it looks like we think of today, so we can draw underneath the outline of the current continent and say, oh, that's where we are today. So there we are, right there. So what we have at this point in time, about 550 million years ago, so the beginning of the Cambrian, is we have the core of the continent, which is above water, so everything in this sort of yellowish color. This is all above water. So this is the old Rodinia, the old continent, supercontinent, what's still above water. It's been eroding for at least 300 million years now, which is a lot of erosion, and it's going to continue to erode, which is why when you go to the central Midwest and a lot of Canada, it's really flat, because it's just been eroding for a super long time. Just offshore, so this is the beach, because remember, it's a nice warm beach, because here's the equator, we're very close to the equator. We have a shallow marine environment, and then farther offshore, and you can think of it here, the beach, shallow marine, and then deeper marine as you get into the ocean. In green here, we've got the deeper ocean. So the kind of sediment that's being deposited in these sedimentary environments is sand at the beach, and then in the shallow water, some of the sand from the beach is going to blow into the water, and you're going to have all that activity, all that marine life that likes warm, shallow water. Just like now, you go to the Bahamas, there's a lot more marine activity than there is off the coast of Maine. So we've got a lot of activity here, a lot of creatures that are making their shells out of calcium carbonate, dying, those shells are accumulating. And then farther off, there is the open ocean where you get much deeper water. But what mostly for us, our area here is mostly sitting in this shallow environment. And the shoreline, as sea level rises and falls, the shoreline is moving farther in and farther out. So you get episodes of sand deposition, episodes of limestone deposition, and that we're just sort of on the edge. So that's where our sandstone and limestone are forming here. So this is what we call a passive margin. When a continent breaks apart and then just sort of pulls like this, the edges of the continents are just eroding and stuff is just being deposited into that basin. There's no volcanoes, there's nothing else going on. It's just the continent is eroding and the sediment is accumulating on the continental shelf and then down into the deeper water. So you get these shallow water sediments, and if sea level is in the process of rising, or if the crust is sinking, because sometimes you can see these are faults, might just be being down dropped, one way or another, you just get an accumulation of sediment, and you get layer after layer after layer of sandstones and limestones and occasionally shales building up, building up, building up, and you get what we see in the whole Champlain Valley, which is an incredibly big thickness of sedimentary rocks. There's several thousands of feet of sediment. If you could take all of the sedimentary rocks and just line them up all in one place, you could, drill down all through all of them, and you'd have several thousand feet, maybe 10,000 feet of sedimentary rocks. There's just a lot. This persisted for millions of years. A lot of time for that sediment to build up. In the early Ordovician, this is another way of thinking about what the world looked like. Again, this is what was land that was exposed, so you can see sea level has dropped somewhat relative to the land, so more of the land is exposed. But again, we're still right on the edge, so there's the beach and the shallow water, so we're largely in the shallow water environment here. Now, there's a line of volcanoes here, which is the leading edge of a collision that's going to occur. So I'll just give you a little hint of that coming up. This is a cross section. So let's just go back for a moment. So imagine cutting a line right through there and separating that and then looking at the side. So that side view. So this is what's going on out to sea. There is an arc of volcanoes, and they're heading in. They are going to eventually close a portion of that ocean. They're going to cause a mountain building event that I alluded to much earlier that caused rocks to our east to be much more affected. The only effect of that is going to be the faulting that we see. We're too far away from the edge, because you see we're out here. So we're still in this nice shallow water environment, limestones and everything forming. We're sitting on that old continental crust, and way out that a ways, there's all this activity. This portion of the ocean is closing, and that's going to cause a lot of metamorphism and everything. But our rocks way out here are so far away, they really don't get affected by any of that, except for the fact that when you squash all these rocks together, it cuts it up into bits, and there's some shoving and jostling going around. One interesting thing that we don't see much of here, but there is evidence very, very close by, is you see how this volcano is spewing ash into the air, and that ash is settling pretty far away, and it works its way into the sedimentary rocks here. And just last summer, I met up with a couple of old friend geologists, both retired, and since I am now retired, you know, just a bunch of old geology codgers walking around in the woods. And what they're still doing some research, and what they're doing is they are looking for evidence of this ash, and where they find it, they chisel out little samples of that, and then they take it to, one of them is retired from Wellesley, and the other one from SUNY Buffalo, and they have connections with laboratories that do the kind of radioactive age dating that I talked about, saying we don't have the right minerals in these rocks. Well, if you get lucky and you catch some of this ash, those do have the right minerals. So we can do some really fine-tuned age dating and figure out the ages of rocks that otherwise you just have relative dates on. So that's kind of cool work that they're doing. All right, so anyway, I just want to give a bit of evidence for this shallow water environment that we see right here on the mount. So what we call the Potsdam Formation, we like to name rocks based on geographic locations where they're first described. And so the sandstone that we see on the Southern Defense Trail on this end of the mount is named after the town of Potsdam, New York, which is where the same rock is found and was very in detail described back in the late 1800s. And so, same rock here, called the same name. So the Potsdam Formation is this sandstone. And one thing that you can see are these really cool worm burrows. If you go down the steps to the southern end, some of the steps have these patterns in them. And these are the burrows that worms made as they were moving through the saturated sand. The burrows get filled with other sediment that's a little different from the sand that they went through, and that's why they weather out differently from in erosion. So there are worm burrows, evidence of very, very, very shallow water environment at a beach. There are what are called stromatolites. The Whitehall Formation is one of the Dolomites. This is sort of in the central part of the mount. And stromatolites are a kind of fossil that's not there's nothing left of the original organism, but this is the result of mats of algae, very, very shallow water, mats of algae, and the algae grow, and they're kind of sticky. And so there are places on Earth where you can see this happening today, like off the coast of Australia. And so sediment that's weathering off or blowing in from the beach gets stuck in that sticky mat, and then the little algae go, wait, we need sun, and they grow up, and they're sticky, and more sediment gets stuck on them. And so these sort of mounds end up growing of these algae mats with the sediment that they trap. When that material gets turned into a rock, the sticky algae disappears, the organic matter just basically evaporates away or gets taken away, but those sedimentary layers, the sticky silt that's mixed in with the limestone now, form these kind of wiggly layers in the rock. So this is evidence of that kind of organic activity, warm, shallow water, probably pretty salty water at that. So we see those here. And then there are two places where we see what's called cross-bedding. And cross-bedding is what you get when you have sediment that's being laid down where there's a current that changes direction. So if you think of a beach with the waves coming up and then going off at a different angle, or the shallow water underneath the waves, you know, you get ripples and you get movement back and forth. And so what happens is the layers of sand get laid down at a very, very slight angle, and then the current changes and you get more being laid down on top at a different angle. So we have evidence, again, that's a very shallow water piece of evidence. At the northern end of the mount, there are a couple of kind of crummy outcrops, but you can see, if you look close enough, that there are layers like this, and then there's layers at an angle like that, and then another layer like this. This is more of that cross-bedding, indicating this changing direction of current, which is typical of shallow water. You can look also very, very closely with a microscope. So you take a piece of rock, cut a thin slide from it, and then use a special, what we call a petrographic microscope that can look through, uses light that shines through it. And you can see in great detail some of the evidence that we also use to figure out how the rocks here formed. So here's our Potsdam sandstone, and what we see here, and the black, white, and gray colors are simply a function of how light is shining through. As you rotate the slide on the microscope, the colors go from white to black to white to black, and that just has to do with how light moves through crystals. So don't worry about the colors as much as the evidence that what we have here are these beautiful rounded quartz grains. You can see these sort of shadows of these rounded edges, and you only get beautiful rounded grains like that when you have sand that's rolling around on a beach for a really long time and it's getting nice and worn down. The rounded edges are now filled in with the quartz that's cementing the sand grains together, but you can see the ghosts of those round sand grains, which really only form in a long-lived beach. Other information we get of a shallow marine, warm, shallow marine environment is from the Ticonderoga formation, which is between the Potsdam, the sandstone. It's the first dolostone. It's a sandy dolostone, and then you get into more limestoney-like rocks as you move farther north here. And there's evidence of other shallow water things. So here we've got these nice round sand grains that got blown into the shallow water. Just, you know, the breezes blew them in. They got incorporated in with the more limestoney-like stuff. In the center here, we've got something called an oolith. And this is, it might be organic, it might be inorganic, but this is the result, again, of particles that are rolling around in very, very hypersaline, shallow ocean water, and you're getting layer after layer after layer of mineral growing around these grains. You can see this kind of thing happening in the Bahamas today. So evidence for that. And then there are these, what are called peloids, these little tiny rounded, and the scale here, I should say, that's 500 microns. So this is 0.5 millimeter in diameter. These are really, really tiny things. But these teeny tiny little dark things here, what we call peloids, and that's probably somebody's fossilized poop. So, little organic stuff, you know, down little tiny, tiny little things. So again, organic activity, shallow water kind of thing. So, is that my last slide? No. So my last slide is just this is what a geologist would present to other geologists. So this is showing the geology, and I've obviously superimposed it on the on a air photo here. And so, in general, I think that there's a fault at the bottom here that's duplicating. You see the Potsdam and the Ticonderoga, and then the Potsdam and the Ticonderoga again. But with that duplication there, just the fault doubling up the thickness, it's basically the sandstones at the end here. And then the farther north you go, you get into the younger rocks, which are more limestoney-like. So this is what it would look like on a side view if you were to cut a line from south to north there and open it up and look at the side. This is south to north. You see these layers of rock that are gently angled, tipping towards the north, so that as you walk across, you can see you go from one rock type to another. And then the fault that goes along here, separating, see it says UD, up, down, so this has come up relative to that. So the other rocks you can think of as the fault being right here, lifting this up base compared to the rocks that are farther to the east here. So I will leave it at that. I think that's enough geology for once, but thank you very much. That'll get you started.
People have questions?
I have a question.
Yeah.
This relates to our next speaker, because there's outcroppings of chert, and where does that come from?
Oh, yes, I should have mentioned the chert. Yeah, it's like, how much do I include and how long do you want me to talk for? Yeah, the chert is fantastic. So chert is, I'm sure you all here know that dark gray, super hard, and it's made out of the same material as quartz, what we just generally refer to as silica, so it's SiO2. There are some marine organisms, they're rare, but they definitely exist, and they still do today, that instead of making their little shells out of calcium carbonate, they make their shells out of silica. And so there are places where you get layers or accumulations of these little tiny critters, and these are all microscopic. They're very, very, very tiny. And so they're making their little tiny shells basically out of quartz. It just isn't a crystalline structure in the same way that you think of quartz crystals. And then when those organisms die, those little tiny silica shells accumulate and they get worked into the geology, as the rock accumulates. So that was going on at the same time. And it's so interesting because we don't really know why chert forms in some places and then not others. And so, as those of you who know more about chert in the archaeological record know, you can tell where the chert comes from. So different chert looks different in different places. And so the chert here, to the best of my now 30-year or 25-year recollection, is largely found sort of in this side. So it's mixed in with the Ticonderoga and the Whitehall formations, these dolostones. But that is just another kind of organism creating another kind of sediment that is accumulating.
Thank you.
Yeah.
There are other questions?
Yes.
Oh, I have a couple, sorry.
Yeah.
No questions. So I love the maps that you showed of like the previous supercontinents.
Mhm.
I remember hearing a lot about Pangaea in school, but you referred to this as Rodinia. Is there
Right, Pangaea was a much more recent one.
Oh.
So Pangaea was the result of all those continents that separated. Rodinia broke up, we have all these oceans forming. 200 million years, 400 million years later, they come back together again, and that's Pangaea. And when Pangaea opens, it's when we get the Atlantic Ocean. When Rodinia opened, the ocean that was formed, that these rocks accumulated on the edge of that ocean, geologists call that Iapetus. And if you know your mythology, Iapetus was the father of Atlantis. You get it? So yeah, we love our mythology. Yeah, so exactly the same idea though. And so there's a theory in geology that this sort of cycle has been going on for all of Earth history. There's a geologist in the early to mid 1900s, J. Tuzo Wilson, who is one of the first people, one of the great minds of plate tectonics, and he theorized this repetitive cycle, and so we call it a Wilson cycle, where you get this coming together of continents, splitting apart of continents, coming together over time, and the periodicity is on the order of, I don't know, 300-400 million years. So it's a long process, but we have evidence that it's happened a number of times. Yeah.
And then my other question, so you mentioned that like radiocarbon and other dating is impossible in these rocks. Is that true for all sedimentary rocks or just?
It's largely true, because the thing is that you might, think of a granite. Granites are beautifully easy to date because they contain radioactive elements in minerals. One of the most common is a mineral called zircon. So all granites have a number of these teeny tiny little zircon crystals. Zircon contain uranium, and it's the uranium that is radioactive that we use to tell how old it was. And we know that a granite forms when a magma, melted rock, crystallizes. So when you get the age of those crystals, that is the age at which that granite crystallized. So let's say you have a granite which is 1 billion years old, and you now start weathering that granite. So it formed deep underground 1 billion years ago, a couple of 100 million years, it's exposed by erosion. Now it's up at the surface, and it's eroding down into, let's say, a beach. And there's a sand that's accumulating on the beach, and that sand is made out of pieces of that granite. So maybe some of the zircons from the granite work their way down. Zircons are very tough little minerals. They work their way down to the beach, and they accumulate in the sand. The sand becomes a sandstone, and then somebody comes along 300 million years later and says, oh, I'd like to get the age of that sandstone. Oh, look, there's a zircon. Well, if you date the zircon, you're getting the age of the granite, not the age of the sandstone. So you need a mineral that is forming at the time that that rock you're interested in is forming. So maybe the cement that's holding the sandstone together, that would be the age of the sandstone. But the cement is made out of quartz, and that doesn't have anything radioactive in it. So it's really hard to date most sedimentary rocks, because if they have something that's datable, it's from the rock that eroded, or they don't have it, or what we often use are sort of secondary processes, like it's like the ash. For example, you have a layer of ash that's fallen into a shallow water environment, and there's limestone on either side of that ash layer, and maybe then there's another ash layer. So the limestone that's sandwiched between those two ash layers, you know its age is younger than this one and older than that one. So we can bracket the age, and that's done a lot. In some places you might have a sedimentary rock that's been cut by an igneous rock, what we call a dike, which is if there's igneous activity and some of that magma shoots up along a fault and then crystallizes, well, we know that the rock it cut across is older than that igneous rock. So if we know how old that one is, because it contains something we can date, we know that the rock is older. So it's a combination of absolute dates and relative dates, and you narrow it down. If you've got fossils, that really helps, because the fossil record has been so well studied and matched against absolute dates that we can say, if you have this particular trilobite, it's this old, and you can nail it down to like within 1 million years or something. So pretty close. Yeah, as we go. If you're talking 500 million years and you can say that that is 372 million years, we're doing really well, right?
I'm just interested, did you get assigned this area to look at, or did you choose it?
Orwell in general, well, when I first got to Castleton in 1992, I worked, the other geologist who hired me was named Andy Rayford, and some of you might know Andy. And so he had been working on a project basically mapping the Orwell Quad, and he never finished it. And he died 3 years after, or 2.5 years after I got to Castleton. And I thought in my naivete at the time, it would be really nice if I could finish Andy's map. And it turns out that, one, he was a much better field geologist than I will ever be, and because it's really complicated geology around here. And I definitely, and I'm not a sedimentary geologist by any means. I used to study ore deposits, so very different kind of geology. I'm a geochemist, and so this was a huge learning experience. It was great, but I was definitely outmatched by the rocks. So I did my best, but that's why I ended up here. I definitely would not have chosen this for any other reason. But I love this area. It's just beautiful. It's a great place to hang out. Yeah.
Great.
So one more question at the back, if we have time?
Yeah.
Okay. It's been a long time since I was in school, but I remember something about glacial compression and glacial decompression.
Yeah.
Is that still going on, or is that?
Yeah, and that definitely happened. I thought about adding some of the glacial history here. The thing about glaciation is that it affects the uppermost fraction of the Earth's crust. But because that's where we live, it tends to take on a much bigger kind of aspect in our imagination of the geology of an area. So definitely when this area was covered by continental ice sheets, so go back 30,000, 40,000 years ago, which, as you can see, is a much smaller time scale than I've been talking about before. It's a bit of cognitive dissonance to switch between hundreds of millions of years and tens of thousands of years. We try. So if you think back when the ice sheets were covering the area, as they were moving southward, they were eroding, and then when they melted, there was deposition. So they definitely modified the landscape. But what they did was they made existing valleys a little deeper, a little wider. They made existing ridges a little sharper, maybe slightly shorter, but they really just superficially modified what was already an existing landscape that much longer time scales and a lot of running water and wind had eroded previously. Now, what you're saying is very true, that when the continental ice sheets, if you have a mile of ice sitting on the crust, that's heavy, and it's going to push the crust down. And in fact, during the last ice advance, that happened here, and what is now the Champlain Valley, which is full of a freshwater lake, was pushed down below sea level. And so when the ice melted at the end of the last ice age, the rock rebounded, but much slower than the ice melted. So the valley was pushed below sea level, the ice disappears pretty quickly, and the crust is slowly rebounding, but when the ice cleared out and opened an opening to the Atlantic Ocean came in, and there was an arm of the Atlantic Ocean called the Champlain Sea that filled the Champlain Valley, Lake Champlain Basin, wider than the current lake is, with saltwater. And so that's why you get things like the Charlotte whale, which is that big whale fossil up in the museum at UVM that was discovered by railway workers in the 1880s or something. So there was definitely an arm of the ocean here. The land slowly keeps rebounding, and then at some point, I think about 5,000, 8,000 years ago or something, I'm not quite sure of the timing, it finally rebounds above sea level, the salt water drains out into the Gulf of St. Lawrence, and then slowly rainwater coming down off the mountains on either side starts filling the lake with fresh water, which is what we have today. So all of that sediment that's related to that is loose. It hasn't been turned into rock, and it's all sitting on these much older rocks. So it's kind of mantling the surface, but it hasn't made its way into the actual rock part of the geology. It's still loose sand and gravel and clay. Yeah.
Real quick, during the rebound, will rocks also, will the rock that's rebounding also crack open in places?
It will, not so much because of glacial rebound, just because that isn't quite. There is some, yeah, there is some. The Adirondacks are a more interesting story in terms of cracking due to uplift. For reasons we do not understand, the Adirondack Massif, that whole big block of, stretching all the way over to Potsdam and areas, all of the high peaks area, it's rising. We don't know why, because those are very old rocks. They have no business actually being up so close to the surface now. And so the Adirondacks are actually, you can do geophysics on it. They've been rising for quite a long time. And as they rise, they also expand as the overlying rock goes away. And there are a lot of very high angle faults. One of them is the one that pushes up, the one I said is underneath Lake Champlain between here and Mount Defiance. That's pushing that up. There's a big fault there that's taking these much older rocks and putting them against much younger rocks. And then there's a whole bunch of faults throughout the Adirondacks. Sometimes if you have two faults like this, the rock in the middle falls down and you get long, narrow valleys. Lake George occupies one of those. Schroon Lake occupies another one. That's why they're these long, skinny lakes, because they're filling these fault-bounded valleys. So there's definitely uplift going on there that's not related to glaciation. It's a bigger process. But yeah, it does crack the rock. All right, well, thank you so much.